We are dealing with a knowledge area chemical change. The topic would be the mole and related concepts. Let's look at the data sheets for this particular section. You are given the constants, right? Let me draw your attention to some of these constants. For instance, in this section you'll be dealing with standard pressure, and here you got pressure, right? And the theta there indicates that it's under standard conditions, and what standard pressure? It is 1.01 times 10 to the 3 10 to the 5 pascals, right? Pascal is a unit of pressure. Sometimes pressure is also given in atmospheres. Then we got molar gas volume at STP, right? STP stands for standard temperature and pressure. What standard pressure? It's 1.01 times 10 to the 5 pascals. And standard temperature is equal to 273 Kelvin. Okay? So you need to know what standard temperature and standard pressure. Okay, so this will be in your data sheet. And that's the volume, the molar volume of any gas at STP is 22.4 decimeter cube per mole. And we know a decimeter cubed is the same as a liter, right? So it can be 22.4 liters per mole. And then we've got Avogadro's constant. Avogadro's constant here is given by that symbol Na, and the value is 6.02 times 10 to the 23 per mole, right? As you can see, it's a reciprocal mole. Normally, the Avogadro's constant has about 8 to 9 decimal points, right? But for our purposes, we will just have it written to 2 decimal points. Right, now let's look at the data sheet here in terms of the formulas that we have, right? Here you'll see you got N, small n is equal to small m upon big M, right? What does it stand for? N stands for moles, M stands for mass, and big M stands for molar mass, which I will draw your attention to, but I just want to show you the equations we have here. Here again we got N. It's the same N as there, right? It stands for moles. N is the same N for that. So this N here stands for capital N, and capital N is the number of elementary particles, and Na is known as the Avogadro's constant, which is equal to that value there. Okay? And then here again we got N again, the number of moles is equal to the volume over the molar volume. And what's the molar volume? I referred you to that, and the molar volume of a particular gas, it occupies 22.4 decimeter cubed. Right, so that's your data sheet. For this particular section, that's your data sheet, and you've got this formula here, which is concentration is equal to moles upon volume of solution. Right, you're not going to remember this when we get to the section, you will, but know that we've got it in the data sheet. And then here, you've got concentration is equal to mass over molar mass and that divided by volume, right? So we will use those formulas when we deal with a section on concentrations. Right, now let's look at the periodic table. So you'll also be given a periodic table in the exam, and as you can see here, if I look at this, that shows us approximate relative atomic mass. It's relative atomic mass, and you can see of copper it's 63.5. Right. And if I'll show you chlorine, and chlorine is 35.5. Why I'm showing you this, these are the only two that seem to be given to one decimal place. All other relative atomic masses are given as whole numbers. You can see the hydrogen is 1, lithium is 7. Normally hydrogen can be given to 4 decimal places, like it could be 1.0001, but we are not interested in that degree of accuracy. So we will, most of these relative atomic masses are written as whole numbers. Right. And you need to also, in these formulas, you need to know what each symbol stands for, right? And in what context you can use it. Okay. And here, like I said, you've got the approximate relative atomic masses. Why relative? Relative because they're relative to the carbon-12 atom. All these masses are relative to the carbon-12 atom. Right? And when it's relative, there is no units, right? And that's important. Relative atomic mass, you can see it's just numbers, and that gives you an indication of the masses relative to carbon-12, but it has no units. Right. And like I said, these relative atomic masses for this periodic table, they're given as whole numbers. Right. Now, okay. Now let's look at atomic mass. Okay. So it is convenient to use a unit called the atomic mass, right? And that unit is given in AMUs, right? And the reason for using atomic mass, because the masses of atoms are extremely small, right? They're extremely small. So when we talk about the mass of an atom, we give it in terms of atomic mass units, right? Okay, so first I said that in terms of relative atomic mass, it's just a number with no units. But if we are expressing it in a unit, then it's expressed in atomic mass units. But see, one atomic mass unit, what's its value? It's 1.66054 times 10 to the minus 24 grams. It's extremely small. So we don't want to say if something has a mass of one atomic mass unit, we don't want to say it's 1.66054 times 10 to the minus 24 grams, because we're dealing with such small values. We then just have an appropriate unit for it, and we call it atomic mass unit. But when we say atomic mass unit, you need to know that one atomic mass unit is equal to 1.66054 times 10 to the minus 24 grams, which we will approximate and say it's 1.66 times 10 to the minus 24 grams. And therefore, 1 gram is actually equal to 6.0221 times 10 to the 23 atomic mass units. Right. So many atomic mass units make up 1 gram. Right, and we're going to be using this number, so you need to familiarize yourself with these numbers here. Right, then the mole. The mole, or the symbol mole, is the SI unit for the amount of substance. Right, it's the SI unit for the amount of substance. Okay, in the past, the mole was linked to the carbon-12 atom. Now, since last year, in May, the mole has been delinked from the mass of the carbon-12 atom. It has now been linked to the Avogadro's constant, right? And so, 1 mole contains, this is now the Avogadro's constant, which says that 1 mole contains 6.0221407 times 10 to the 23 elementary entities. Right, that's a fixed number, and that's an exact number, right? And as I showed you on the data sheet, we will just use it as 6.02 times 10 to the 23, but this number here is a fixed number and it has been defined. Right, and the Avogadro's constant is one of the natural constants that have been adopted by the SI. Then we said, all right, it has the elementary entities, right? Now, what are the elementary entities? An elementary entity can be an atom. So if I say 1 mole contains 6.02 times 10 to the 23 elementary entities, and if my elementary entities is elementary entities in atom, if I talk of 1 mole of atom, then I mean it must be 6.2 times 10 to the 23 atoms. If I talk of molecules, then 1 mole of molecules, then it must be 6.02 times 10 to the 23 molecules. If I talk of an ion, could be sodium ion, potassium ion, chloride ion. If I talk of 1 mole of an ion, I am saying it's 6.02 times 10 to the 23 ions. And if I talk of an electron, then 1 mole of electrons would imply 6.02 times 10 to the 23 electrons. Or any other particle, right? Or a specified group of particles. So if I say I want 1 mole of eggs, how many eggs do I want? I want 6.02 times 10 to the 23 eggs. If I say I want 1 mole of apples, how many apples do I want? I want 6.02 times 10 to the 23, 10 to the 23 apples, right? So the mole is important. The mole is a counting number, right? But by proxy, we mass it. What am I saying here? That the mole is a counting number. So if you ask somebody for a mole of something, they're supposed to give you 6.02 times 10 to the 23 of that something. But what we do, instead of counting it, we can mass it, right? That means we can determine the mass, and if we give them a certain mass, then we can say, okay, this mass has this amount of elementary entities in it. Right, so let's look at this. Here we've got, for instance, right, we've got here on this particular balance here, somebody say you are asked for 6.0 2 times 10 to the 23 atoms of carbon. Right? So you got your element carbon and somebody wants 6.02 times 10 to the 23 atoms of carbon. Now you don't want to count this, because if you're going to count it, and let's assume hypothetically you counting and you're saying 1, 2, 3, 4, and if you have to count 6.02 times 10 to the 23 atoms, then you will count it, and by that time, you'll be after 100, or say you live up to 70 years, you will die, and your child will count it, and your grandchild will count it, and your grandchild's child will count it, and you still, it's going to take a long time to count. So what we do is we measure the mass, and you measure the mass, and you say, all right, here's 12 grams of carbon. And if you get the mass of 12 grams of carbon, what you can then say, this 12 grams of carbon has got 6.02 times 10 to the 23 atoms of carbon. Right? So in order to know what mass we have to have in order to get 6.02 times 10 to the 23 elementary entities, we need to know the molar mass of the various substances. Okay, we'll get to that. But now, this number is a fixed number, right? 6.02 times 10 to the 23. And that's the value of the Avogadro constant, Na. And it is expressed in the unit per mole, which I showed you in the data sheet, right? So I'm just showing you here again. All right. So, and it is called the Avogadro number. Right now, the mass in grams of 1 mole of a substance, is called the molar mass. Right? The mass of 1 mole of a substance, right here, I've shown you above here, right, that the mass of 1 mole of a substance is called a molar mass. So 12 grams is the molar mass. Why? Because that 12 grams contains 6.02 times 10 to the 23 atoms, right? And the molar mass in grams of any substance, right? The molar mass in grams of any substance is always numerically equal to the formula weight in AMU. Right, so I'll refer you to this and see what we mean by that. All right, so you take the formula weight of the substance in AMU, you can then express it in grams, then you got the mass of 1 mole of that substance. Right? So here now we say determine the relative mass of an H2SO4 molecule. Right. Now, if you want the relative mass of H2SO4 molecule, how do we get that? Right. We say, okay, we have now this is equal to, we know, H2, so it's 2 of H. Right. 2 of H. There's 1 sulfur, so it's 1 of sulfur, plus it has 4 of oxygen. Right, isn't it so? It has 4 of oxygen. Right, now we want to know what is the mass of hydrogen. So it's 2. What is its relative atomic mass? Right, if we want to know its relative atomic mass, we go here and we say, okay, its relative atomic mass of hydrogen, and we look at it and we say, okay, it is 1. Then we would want to know what is the relative atomic mass of sulfur, and if we look at sulfur, right, if you look at sulfur, and sulfur is 32. Isn't it so? And if we look at oxygen, what is oxygen? It's 16. Right, so we've got, and these are all relative atomic masses, okay? So if we look at this here now, hydrogen we said is 1, okay? And sulfur is 32 plus, okay, 4 times 16, we know is 64, and that then gives us 98. Right? 98 is a relative atomic mass of one molecule of H2SO4. Right? And there is no units. Right? No units. Relative atomic relative masses are dimensionless. Right? But if we want to express that mass in, numerically, right, and we need to express this formula or that formula weight, like we said, in AMU, right? So if we have this and I want to determine the mass of sulfuric acid in atomic mass unit, when we express this in atomic mass units, we then say, all right, firstly, it would be also 2 of hydrogen, right, plus 1 of sulfur, plus 4 of oxygens. Right? The same thing as above. But now, for molecular weight, we can use this formula. Sometimes it's, we write it molecular weight like that, and of H2SO4, right? Which is equal to, right, that part there. But if you want to know, and we do the write the numbers in, so it's 2 times 1. So now, because we're dealing with the atomic masses, we say 1 atomic mass unit plus sulfur is 32 atomic mass units plus 4 times 16 atomic mass units. Right, so now I'm not giving it in the relative terms, I'm giving it in atomic mass units, which then means this is a 98 atomic mass units. Right, so the mass of one molecule of H2SO4 is 98 atomic mass units. Right, and we know that an atomic mass unit is equal to this value here, right? And if I want to express it in grams, then I have to multiply by that particular factor. Right, so now let's say I want the mass of sulfuric acid not in atomic mass units, but I want it in grams. So just to get a sense as to what is its mass in grams. So if I have the weight or the molecular weight of H2SO4, we know that it is equal to 98 atomic mass units, right? But if I want it in grams, then, but say mass in grams, right? is equal to 98 times what's my atomic mass unit? 1.66 times 10 to the minus 24 grams. And when you multiply that out, it gives you 1.63 times 10 to the minus 22 grams. Can you see how light that sulfuric acid molecule is? Its weight is 1.63 times 10 to the minus 22 grams. So that's for one molecule. Right, so we know what's the mass of one molecule. But now what we don't want the mass of one molecule. We want the mass of 1 mole of sulfuric acid. And if I want the mass of 1 mole of sulfuric acid, I know that 1 mole is 6.02 times 10 to the 23 molecules of sulfuric acid. So what's its mass? Now let's work that out. Alright? Okay? Right. Now let's see that. So we want a mass of 1 mole. Alright, we want a mass of 1 mole, and we know a mole contains that, and we want the mass in grams. Okay. But we want it of 1 mole. So we say, alright, now we know the mass of 1 mole, right, is, if we say we want the mass of 1 mole, which would mean we got a mass of 1 molecule is 98 AMU, correct? But if we want a mass of 1 mole, that means I want a mass of 6.02 times 10 to the 23 molecules, right, of H2SO4. Which would mean I know I've got 98. AMU, I know, is times 1.66 times 10 to the minus 24 grams times 6.02 times 10 to the 23 molecules of it. And what does this give me? This actually gives me 98 grams. There you have it. So look at this. If we know the relative mass, which is 98, if I know what the mass of 1 molecule is 98 AMU, so what if I want to know the mass of 1 mole of a substance? What do? I said the molar mass in grams of any substance is always numerically equal to the formula weight in AMU. Right. And they have illustrated that point. So here you have it. And what is a mass? You take the formula weight and you express it in grams. So it's 98 grams. Right, 98 grams. Okay, 98. Okay, it's 98 grams. Okay, so it's 98 grams. But, so you'll say, but alright, so what I'm saying, if you multiply this whole thing out, you're going to get 98 grams. And the reason for it is because if you multiply 1.66, right, times 10 to the minus 24 by 6.02 times 10 to the 23, what do you get? You get 1, right? You get 1 gram, right? And therefore 98 times 1 gram is 98 grams, right? There you have it. So you need to be able to see that if you have the atomic mass unit and you multiply it by 6.02 times 10 to the 23, your atomic mass unit for the and if you express that in terms of grams, you're getting now the mass of 1 mole of the substance. Right. Now let's look at, it says determine the atomic mass and the molecular mass in AMU. Right? Or molecular mass in AMU. Why? Got atomic mass and molecular mass because when I'm dealing with an atom, it's going to be atomic mass. So we want to know what is the atomic mass of copper in AMU. Right? We know that the periodic table gives us a mass, the relative atomic masses. Right? So, but we want to know it in AMU. So here we have this again. So let's erase that. And where is copper? Here's copper, right? There is copper. Here we have copper. And what is its mass? Its mass is 63.5. So its mass is 63, relative atomic mass is 63.5, but if we express it in atomic mass units, then it's 63.5 AMU. Okay. Alright. Alright, so now we have that. Okay, so here it would be that would then be equal to that would be equal to that would be equal to 63.5 AMU. That is its atomic mass unit. If I obviously wanted this in grams, then I must multiply by 1.66 times 10 to the minus 24 grams. But here we just want it expressed in atomic mass units. What is the molecular mass of of copper sulfate and 5 hydrates? So we say copper sulfate pentahydrate, right? So if we have to look at this in a periodic table, we will see that, okay, we got copper. Copper is 63.5. If we look at sulfur, we know sulfur is 32. If we look at oxygen, we know oxygen is 4 times 16. Correct? Plus, if we look at now, we got 5 H2O, which means it's 5, correct? Times, I'll just do this in one step. We know hydrogen is 1, so there's 2 plus oxygen is 16 is 18, so it's 5 times 18, right? And that in atomic mass units would be equal to 249.5 atomic mass units. Right, that is the mass of copper sulfate pentahydrate. But if I want it in grams, then I have to multiply it by 1.6 6 times 10 to the minus 24 grams. Right? But if I want the mass of 1 mole of the substance, then we take this atomic mass unit and express it in grams. which would mean that the molar mass or the mass of 1 mole would be 249.5 grams. Now let's look at sulfur, right? Sulfur, if we look at sulfur, sulfur would be 32 AMU, right? Let's look at sodium hydrogen carbonate. If we look at sodium hydrogen carbonate, we know the sodium hydrogen carbonate is Na. I'll do this here, and we know it is H, plus we know it's 1C, and we know we got 3 of oxygens. Isn't it so? So if we want to find out what is its atomic mass unit, we know that's 23, we know that's 1, we know carbon is 12, and we know oxygen is 16, right? But we got 3 of it, so it's 16. And what does that give us? That gives us 84 atomic mass units. So one molecule or one formula unit, right? Remember when we deal with molecular substances and we refer to the formula as we refer to the substance as having molecules. When we deal with ionic substances, we refer to it as having a formula unit, right? So that is 84 atomic mass units. Now let's look at C6H12O6. If we want to know what is its atomic mass unit, then we say, okay, carbon would be, right, 12, but we got 6 of it. So it's 6 carbons and 12, correct? Plus we got 12 hydrogens times 1. Plus we got 6 oxygens times 16. Right? And what does that give us? That gives us 180 AMUs. Right? You check the periodic table and you'll see it gives you 180 AMU. So what am I saying here? I am saying one molecule of C6H12O6, right, has a mass of 180 atomic mass unit. All right, let's look at mercuric oxide. Mercury oxide is, okay, mercury is not a very common element in the sense that we don't know its mass. Let's go and see what its mass is, right? There we go, and let's look at mercury. Let's see mercury, right? If you look at mercury here, mercury has an atomic mass of 201. Right, and it has been rounded off. Normally it's 200.75 or whatever, but here it has been rounded off for us. Okay, so we then use a rounded off value. Okay. Okay, there we are. So mercury, we would then have, right, mercury is equal to, then if you look at this, right, mercury would be 201 AMU, and plus oxygen is 16 AMU, which then gives us 217 AMUs. Right, that is a mass of one formula unit of mercuric oxide, right? or we could have said 1 molecule of mercuric oxide, right? But because it's an ionic substance, we refer to it as a formula unit. Right, so there we have that, and let's go to the next one. Now if we look at sodium chloride, we know sodium chloride, okay? Sodium chloride is 23, and I showed you chlorine is 35.5, and which is then expressed in AMUs, it will be 58.5 AMU. So these are all masses given in AMUs, right? But now let's see. Now we want to express it in terms of molar mass, right? And molar mass, the unit of molar mass is grams per mole, right, of the following. So we want to determine the molar mass in grams per mole of the following, right? So if we want to know the mass of 1 mole of the substance, right? Not the, when I am speaking of the molar mass, I mean the unit is gram per mole. But here, when I say determine the mass of 1 mole of the substance, right? Determine the mass of 1 mole of the substance. Okay, so if we want to determine the mass of 1 mole of the substance, I should determine, I think I should have said here, determine the determine the mass of 1 mole, right, of the following, right? So the mass of 1 mole is essentially the molar mass of the substance, right? But here I'm just going to give you the answers in grams. So if we look at copper, what's copper? Copper is 63.5 AMUs. And what did our form earlier when I drew your attention to it? That's for 1 particular atom of copper. So what's the mass of 1 atom of copper? Is 63.5 AMU. What is the mass of 1 mole of copper? It is 63.5 grams. So we got the formula, the atomic mass of that molecule. If we want the mass of 1 mole, that means I want a mass of 6.02 times 10 to the 23 elementary particles. In this case, the elementary particle is an atom. I have to have a mass of 63.5 grams, and then I can say it contains 1 mole of that particular substance. And then copper sulfate, what would its mass be? It would be then 249.5 grams. So it would be 249.5 grams. So we take its atomic mass unit and we express it in terms of grams. So here 1 mole of copper sulfate pentahydrate will contain 6.02 times 10 to the 23 copper sulfate pentahydrate molecules, right? For sulfur, it would be 32 grams. And for sodium bicarbonate or hydrogen carbonate, it is 84 grams. Okay. And for this one, it's going to be 180 grams. So 180 grams implies that it will be having 6.02 times 10 to the 23 molecules of C6H12O6. There it would mean that would have 6.02 times 10 to the 23 molecules of that. This one implies that it will have 6.02 times 10 to the 23 atoms of sulfur, right? Because we're dealing with an atom. There we're dealing with an atom. Here we're dealing with a molecule, right? Here we're dealing with a molecule. There we're dealing with a molecule. Same thing, yeah, I could talk of it as a molecule, or I could speak of it as a formula unit. And this would be 217 grams, right? Will contain 6.02 times 10 to the 23 HGO molecules or formula units. And then NaCl would be 58.5 grams, right? And this will contain 6.02 times 10 to the 23 NaCl. Remember when we did NaCl, ionic substance had ions in the ratio 1:1, right? And that was an ionic compound, and we said we don't have a discrete molecule, so we refer to it as ionic compound, and we refer to it as a molecular unit. Right, now here it's given to you nicely. Here is I have, for instance, there's mercury, which is HGO. I showed you that, and we calculated that to be 217. So if I have 217 grams of mercuric oxide, what can I say? I can say I've got 6.02 times 10 to the 23 molecules of HGO in here. If I take 180 grams of sucrose, right, I can say in 180 grams of sucrose, I've got 6.02 times 10 to the 23 molecules of sucrose. If I take 32 grams of sulfur, then I can say 32 grams of sulfur, right, contains 6.02 times 10 to the 23, right, atoms of sulfur. So, I mean, as you can see, right, 216 grams, 180 grams, 32 grams, and here we got copper sulfate, pentahydrate, right? And here I've got 58.5 sodium chloride, and here I've got copper, which is 63.5 grams. So what's common in all of that? All of those, with their respective masses, all of them have each of them have 6.02 times 10 to the 23 of those elementary entities. If I'm dealing with a molecule, that's the amount of molecules it has. Like this will have a molecule, that would have molecule. If I'm dealing with sulfur, sulfur will have atoms, right? And if I'm dealing with copper, copper will have atoms, right? So there you have it. All right. Now, if we look at the molar masses, Okay, if you look at the molar masses here now, let's look at that. So, molar mass and formula masses. Okay, here we got N is equal to the amount of substance, right? Is equal to the amount of substance. Mass is the mass of the sample, and M is the molar mass of the substance, right? So if you remember earlier, I had spoken about the mole of the substance basically because I didn't yet introduce the concept of molar mass. So here, molar mass is the relative mass of 1 mole of a substance expressed in grams, right? And if we're dealing with an element, then it is a mass per mole of atoms. If I'm dealing with a molecular compound, then it's a mass per molecules. Or if I'm dealing with an ionic compound, then it's a mass of the formula unit. Right, now let's look. N, or the number of moles, the unit of it is mole. Molar mass, the unit of it is grams per mole. And mass, the unit of it is grams. So you need to know what the unit of each one is. So if you look at this, you will see, I can draw your attention to this, not here, there, and remember I said you'll need to know these formulas. There you have it. So here you have this particular formula, which means here we're going to be dealing with that formula. N stands for moles, M stands for mass, and big M stands for molar mass. Okay, so we have that, and we can then we have that. Okay. So now, let's see if we can apply this particular formula here, right? Here it says, determine the moles of 198 grams of nitric acid, right? So, if we want to apply that, we say, okay. If you want to know nitric acid, so we say, all right. And you'll get that formula on a data sheet. So we say, okay, N is equal to mass, right, over the molar mass. So I normally like to write it like this, HNO3, right? And what's the molar mass of HNO3? We have to get that. And how did we say? We get the formula mass and we express it in grams. Right. So what is its formula mass? Let's look at it. We know hydrogen is 1 plus nitrogen is 14 plus we got 3 times oxygen is 16, like that. Isn't it so? And what does that give us? We know that this whole thing is going to give us 63, right? 63 AMUs, which we express as in grams, so it becomes 63 grams. And since the unit of molar mass is grams per mole, so this is 63 grams per mole of nitric acid. So if we look at this, but we are given 189 grams, right, upon 63 grams, right, per mole. That cancels out. Mole per mole goes up as mole, and that gives us 3 moles. So 189 grams of nitric acid contains 3 moles of nitric acid, right? And we know a mole, how many molecules would it be? 1 mole would be 6.02 times 10 to the 23. 3 moles would be 3 times that amount. Okay. Right, let's look at the next one. Determine the mass of 2 moles of KClO3. Okay, so we want to determine that. So we say, okay, N is equal to mass upon molar mass of KClO3. So if we want to determine that, we say, okay, M of KClO3, what's it equal to? It's equal to K, right? Equal to, so K is equal to 39. Chlorine, we know, is 35.5, right? And oxygen is plus 3, right? Times 16, okay? And that is a molar mass of potassium chloride, right? Which is, how much is it equal to? 122.5 grams per mole. That is what it is, right? So, if we want to know, it says calculate the mass. So we say, okay, N is equal to mass upon molar mass, but we want mass. So mass is equal to N times the molar mass of KClO3, which means how many moles are we talking of? 2 moles. Right? What is molar mass? It's 122.5 grams per mole. Mole cancels out. What are we left with? 245 grams. So what we're saying is that 2 moles of KClO3 has a mass of 245 grams. Right, let's look at the next one. Determine the moles of 11 grams of carbon dioxide. Right. So if we want a mass of 11 grams of carbon dioxide, the moles of 11 grams of carbon dioxide, so we say, okay, we start again. N is equal to mass upon molar mass of CO2. Then we say, okay, what is M of CO2? We look in the periodic table and we say, okay, I know carbon is 12, plus I got 2 of oxygen, which is 16. So in total, it's equal to 44 grams per mole. Okay, 44 grams per mole. Now, if I want to know what is the mole of 11 grams, so it's going to be 11 grams upon 44 grams per mole, right? Which means that cancels out and mole goes on top as mole, and 11 upon 44 is 0.25 mole. Right, there you have that one. Okay, now let's go to the next one. It says calculate the moles of glucose in 5.380 grams of the substance, and we dealt with this earlier. So N is equal to mass upon molar mass of C6H12O6, correct? But what is M of C6H12O6, right? And if we work that out, we know that here we got 6 times 12 plus 12 times 1 plus 6 times 16, right? And we did it earlier. We know that gave us 180 AMUs, which we then express in grams, and here the molar mass is 180 grams per mole. Right, so if we want to know how much is 5.380 grams, and we say okay that, and we divide by 180 grams per mole, right? And we know that cancels out, and what do we get? We then get that is equal to 0.0299 moles. Right? Then let's look at the next one. If we look at the next one, it says calculate the mass in grams of 1 mole of glucose C6H12O6. So that straightforward. Here, just want you to be able to apply this. So we want the mass of 1 mole of glucose, and we know what its mass in atomic mass units is, which is 180, right? So it's actually that, right? So we know it's actually that. So what's its mass? The mass in grams of 1 mole is 180 grams, right? There's the mass in 1 mole. Here I said what is molar mass, then the unit would be 180 grams per mole. Yeah, I just want the mass in 1 mole. Okay, let's go to the next one. Calculate the mass, okay, of 0.433 moles of calcium nitrate. Okay, so obviously you have to know what the formula is for calcium nitrate. So N is equal to mass upon molar mass of CaNO3 2, right? And M of CaNO3 2 is equal to, if we look at that, it is equal to right, it's equal to, so we have to look at calcium, so that would be equal to, calcium is 40, right, plus we got, so maybe let me write it out like this. Let's write it out like this, which would mean this implies 1 calcium, it implies 2 nitrogens, and it implies 6 oxygens, right? But we know calcium is 40, plus we know nitrogen is 14, plus we know oxygen is equal to 6 times 16, which means in total that is equal to 164 grams per mole. That is what it is. There's the molar mass of calcium nitrate. Right, now we want to know what mass in grams. So if we want to know the mass in grams, So mass in grams is equal to N times molar mass of CaNO3Z. So N is equal to 0.433 moles times 164 grams per mole, right? Which is then equal to 71 grams. Right, which is then equal to, sorry about that. Which is then equal to, just erase it properly. Which is then equal to 71 grams. Right, that is a mass of 0.433 moles of calcium nitrate. Right, now we go on to molar gas volumes. Right, 1 mole of any gas at STP, now I drew your attention to this in the data sheet, occupies 22,4 decimeter cubed, right? As you can just to draw your attention back there again, there we go, right? I showed you this and we said that there we have it. At STP, molar mass of the gas at STP is 22,4. Right? And then we said at STP is standard pressure and standard temperature. So you have it here and be aware of that. Okay. Right, now here we got the molar volume of a gas. So we're saying 1 mole of any gas at STP occupies 22,4 decimeter cubed. Right? That's what the law says, or the rule says, or the principle says. Right? So here we have it. If I have neon gas, say neon gas, right? It's a monoatomic gas. If I have 20 grams of neon, right? And if we go and look at this atomic mass, we will find that it's 20. Its relative atomic mass is 20, which we then know it's atomic. If we want the mass of 1 mole of it, we express that in terms of grams. And here's oxygen. Oxygen is 32 because it's diatomic. And here's carbon dioxide. So if I have 20 grams of neon, or if I have 32 grams of O2, and I have 44 grams of CO2, what do I know? They all occupy 22.4. So I told you 1 decimeter cubed is equal to 1 liter, right? And here the pressure is 1 atmospheric pressure, or which is given there in the data sheet as 1.01 times 10 to the 5 pascals. Right? That's given in terms of, this is actually in terms of the SI unit. Here in the old earlier we used to just refer to it as 1 atmosphere. So 1 atmosphere, atmospheric pressure is equal to 1.01 times 10 to the 5. And then we're saying the temperature is 273 K, right? And each of them is 1 mole. Right, so 1 mole of any gas at STP occupies 22,4 decimeter cube. Right, now let's look at the relationship between moles, volume of a gas, and molar volume of a gas at STP, right? And STP stands for standard temperature and pressure, and this what standard temperature and pressure is given in given on your data sheet. So here we have this relationship: number of moles is equal to volume of a gas sample divided by the molar volume, right? So at STP is 273 K or 0 degrees Celsius, and here is given in kilopascals. The pressure is 101.3 kilopascals, or 1.01 right, times 10 to the 5 pascals. Right, so N is equal to V upon V for the molar volume of the gas, and we know that the molar volume of the gas is 22.4 decimeter cubed. And this formula, you'll also get it on your data sheet. Right, now let's look at the first one. Determine the mass of 5,6 decimeter cubed of CO2 at STP. Right, so if we have, for example, N, right, N is equal to V upon Vm, right, which is then, that is equal to 5.6 decimeter cubed, all divided by 22.4 decimeter cubed per mole. I see the units, and that would then be equal to decimeters. Decimeters cancel out, and that the mole, it becomes then mole when we bring mole minus 1 on top, and that is equal to 0.25 moles. Right. Okay. But we want to know the mass. So if we want to know the mass, we know the relationship N is equal to mass over the molar mass of CO2, right? And we know that mass, or the molar mass of CO2, is equal to carbon is 6 plus carbon is 12 plus 2 times 16 for oxygen, which gives us 44 grams per mole. So if we want to now know the mass, which means M is equal to N times M of CO2. Right. If we have that and we want to determine the mass, which means 0.25 0.25 moles, right, which we got from there, and times 44 grams per mole, right, which then gives us 11 grams. Right, so the mass of 5,6 decimeter cubed of CO2 at STP is 11 grams. Right, now let's look at the next one. Here we need to calculate the volume of the following gases at STP. All right. So if we need to determine the mass of 2 moles of carbon dioxide, so we know N is equal to volume upon the molar volume of CO2, right? And I use this notation to say it implies, so it implies V is equal to N times Vm, which is the molar volume. N is equal to 2 moles, right, times the molar volume is 22,4 decimeter cubed per mole, right? Mole cancels out, therefore the volume is 44.8 decimeter cubed. All right, that's A. Let's look at B. We want to, so 44.8 decimeter cubed, right? Now we want to know what the volume would be for 3.3 moles of H2. What volume would it occupy at STP, right? So again, N is equal to V upon Vm, right? Which implies that V is equal to N times Vm. Okay? And which is equal to N is 3.3 moles, right? Times the molar volume is 22,4 decimeter cubed per mole. That cancels out. We left with decimeter cubed, and that is 73.92 decimeter cubed. So that would be the volume of 3.3 moles of H2. Right. Then we're looking at what would be the volume of 0.45 moles of neon, right? Neon is a monoatomic gas, right? So here C, we got again N is equal to V upon the molar volume, and which then implies that V is equal to N times Vm. N is equal to 0.45 moles times the molar volume is 22.4 decimeter cubed per mole. Mole cancels out. We left with decimeter cubed, and that gives us 10.08 decimeter cubed. Right. Now, let's look at the next one. We need to calculate the moles of gas of the given volume, right? for each substance, right? We want to know the moles of gas given the volume, the following volumes. So 150 decimeter cubed of oxygen, right? What moles does this gas have, okay, at STP? So which means if we have this, we got A, right? N is equal to V upon Vm, right? Okay, so right, so I would have added here at STP, right? So N is equal to that, which would mean it's equal to 150 decimeter cubed, right, of oxygen, and we know that the molar volume at STP is 22.4 decimeter cubed, right, per mole, which means that decimeter cancels out, and that gives us 6.7 moles. Right, that is the moles of the gas of 150 decimeter cubed of oxygen. All right, now let's look at the next one. B, we need to determine 145 cubic centimeters of CO2, carbon dioxide. So again, N is equal to V upon the molar volume of carbon dioxide, right, which is equal to, now it's 145 cubic centimeters, 145 cubic centimeters. To convert it to meters, we multiply by 10 to the minus 3 decimeter cubed, right, to convert it to decimeter cube. And the volume of the gas at STP is 22.4 decimeter cubed per mole, right? We know that cancels out and that cancels out, so we balance with mole, right? And that gives us 0.0 that gives us 0.0065 moles, okay, which is then equal to 6.5 times 10 to the minus 3 moles. Okay, and there you have it. Right, see you the next time.